Okay, so we're going to prove the fundamental theorem of calculus part 1. And the first thing we want to do is, of course, understand exactly what the theorem is stating. So basically, if we start off with some continuous function on an interval, a, b, with an antiderivative, capital F, then the following equality is true. That the integral from a to b of f of x dx is equal to the antiderivative of f evaluated at b minus the antiderivative of f at a. Now, to prove this, we want to investigate this here. This is the key, this integral. So what we're going to do is we're going to take a partition of the interval a comma b. Now, a partition is basically just if you break it up into some number of pieces, that interval. So here's a, here's b. And a partition is essentially that you start off with x0, you end with xn, and you've broken it up into n parts. When you start doing this dividing, you just sit here and you say this is x1, x2, x3 maybe, and dot dot dot, xi plus 1, and then so forth, and you go all the way down into n, and now you've broken it up, this interval, into n pieces. Now I'm going to draw this a little bit bigger because we're probably going to need more space to illustrate exactly what's happening. So let's actually go through this area and let's see these pieces all fit together in the right way. So I'm going to draw a bigger set. I'm going to say this is A, which is x0 in my partition, and then this is xn, which is B. So I'm going to start off with some partition of P. Let's say it's given by A is equal to x naught, and then that's less than x1, which is less than x2, and then you go less than dot dot dot, and you keep going, less than xn equal to b. And basically that'll be my partition. Now, for any interval, right, so I'm gonna, illustrate this a little bit more clearly on the graph, that you have a whole bunch of intervals here, right? x1 from x2 is an interval, right? From x1 to x2. This is an interval, right? And you have another interval. You have from x2 to x3, right? And you could generalize this idea saying that the interval xi to xi plus 1, right? Okay, so there's going to be, for n, there's going to be xi plus 1, where I could essentially be anything from 0 to n minus 1, right? This I, right, in this interval could be any of the i's from, again, 0 to n minus 1, right? And that's what's nice. This is a general interval here. This is general, right? So on your general interval, okay, what will apply is mean value theorem. So why will mean value theorem apply? So we need to remember what mean value theorem states, and we need to make sure that we could actually apply it here. So we have now some interval. There we go. We have now some interval xi to xi plus 1. And I have this here. And again, this is going to start off with a, b, and then again some general interval. And you could apply mean value theorem to this interval. Why? Because, okay, you could apply mean value theorem applied to the function f, capital F. Why? So what am I saying here? Let's state mean value theorem and let's put it in perspective. So mean value theorem states if, let's write it f is continuous, and we need differentiable for mean value theorem. And we do have differentiability for this. Differentiable on A comma B, then there exists some C contained in that interval where the following equality is true, with f prime of C is equal to f of B minus f of A over B minus A. Now, this is mean value theorem, and basically we have all the conditions that we need. Why do we have the conditions that we need in our instance? So I'm applying this to capital F. That's why I wrote this capital F. So in this instance, right, this interval takes the role of this interval. Capital F is like the capital F that I have, and then f prime is going to be lowercase f, the actual integral that I'm trying to determine. So what does it mean? What does it mean? Let's write this down here. Let's just apply mean value theorem. So by mean value theorem on capital F for the interval for, right, we have, what's the statement? The statement's going to be that f, there exists some, and I'm just going to call it zi to indicate the interval that it applies to, in this interval with this equality holding, right? With f prime of z sub I is equal to f of xi plus 1 minus f of xi over xi plus 1 minus xi. Right? So this is the key thing here, because f prime, capital F prime, is little f prime. So I could write this again as f of zi is equal to capital F of xi plus 1 minus f of xi over xi plus 1 minus xi. And this is going to be key, because now I need to manipulate this a little bit. So I'm going to get another page. And basically what I'm going to do now is I'm going to say, okay, so I have f of zi equal to capital F of xi plus 1 minus capital F of xi over xi plus 1 minus xi. And this is for any interval along this integral. So again, I applied this to a particular interval, right? Or I mean any interval, I should say, in my partition. So this is xi. This is xi plus 1. In this interval, right, I'm going to have this being true. Okay? And what I can do here is I can multiply by the denominator on both sides. And I get a very relevant equality. And again, this will apply for any interval in my partition. So this equality on the left, this expression on the left-hand side, we should sort of understand what's happening now, because now we need to get into the definition of what an integral actually is. So here's my function f, right? It's going, and I want the integral from a to b, right? So I want this whole area basically. And if you look at this here, right, this is the partition xi to xi plus 1. And we know from the mean value theorem that zi is somewhere in here, right? So f of zi is exactly this value up here, right? That's f of zi. And then this here, so f of zi is this length, and then this length is, so here, xi plus 1 minus xi is this length, right? And then zi is the height. So the multiplication of the two gives you the area of that rectangle that I just drew. And that's very relevant when we're computing integrals, especially when it's a piece of a partition, right? It's a part of the partition. Because what we can start to do is we can start to relate this to the actual integral. How do we do this? So the first thing that I want to do is I want to illustrate with a larger picture maybe, which is just that it's going to look like this, let's say. So let's say again, B, and here's the beginning of my partition, here's the end. What I basically want to illustrate is that there's two ways that we could start summing our rectangles to get our area, right? We could take the lowest value in any partition. So let's say here's x1, x2, and then I'm going to go somewhere xi plus 1, and then I'm going to go somewhere over here, xn minus 1, whatever. It's going to be looking like this, and then I'm going to have my function going across this whole thing. Let's make it look something like that. And then what you want to see is that there's generally two ways that you could look at any rectangle here. So I could find the area underneath the curve by taking the largest height in any interval. So I could say that, the largest height for this interval might be the endpoint at xi plus 1, in which case I would take this integral. But I could also take the lower one, right? So the lower one would be this one. Okay? So, and I could do this for all of them. So basically the orange area could represent the lower rectangle. So what does the lower rectangle look like? In this one, it probably looks like this, right? And I do this for all of my partitions. Maybe it looks like this again for the next one. What's the lowest one in this one? Probably this one. And I could sit here and get the lowest for any of them, right? And that'll be called the lower area. Right, so the orange is the lower area, right? So the lower area for this partition, okay, and I'm gonna write it as the lower area of f of this, given this partition, has to be less than or equal to something else, but it's less than, so we're gonna put something in the middle here that's very relevant. Okay, so it has to be that it's less than, for sure, on the far end, on the far right. If I take the height at the top, right, where this is the blue rectangle, right, is the highest point that I can take in any partition, in any interval of my partition. The partition is fixed. That would be called the upper area for this partition again. And these two values must be squeezed between the sum of all of these values. So in any xi, right? So where's z essentially? Z is going to be, right, in somewhere in here, right? This is zi. And it might not be the lower, it might be less than the lower, and then I have something that looks like that, but let's make this a little more clear. Let's use, I don't know, that color looks nice. Okay, so I have this, right? That's the area, that's this, right, in this case. And I want to sum over all of these intervals in my partition. So basically the sum as I starts off at 0 and goes to n minus 1 of f of zi times xi plus 1 xi plus 1 minus xi. This sum, right, we should see is guaranteed to be squeezed between these two, right? Because if I do it here, zi is somewhere, f of zi is going to somewhere be between the lowest possible value on this interval and the highest possible value, where it could be equal, but it doesn't matter because I have the equality here, right? So it could be equal, which is fine, but f of zi will be somewhere between the max point in that interval and the low point in that interval, which makes this area somewhere between the area of the low rectangle to the high rectangle, right? The lower area rectangle to the higher area rectangle. And I do this for all the intervals. And that's going to be true for any rectangle that I pick. So this goes between the two. Okay, and that's extremely key because what basically we're going to say is that for any partition now, and you want to make it so your partitions are as fine as possible, or as thin as possible, or that n goes off to infinity. Okay, and what will happen is that you want to make this, you want to find the largest possible lower area. You want to find the largest possible lower area, where for each interval, I'm taking the lower end, and I want to find a partition that maximizes that area. So as I get thinner and thinner, the difference between these two will become less and less. And the way we talk about that is we say that it's the lower Darboux integral of f which is what I just defined for this one, which is that it must be, okay, that I want to find of all the partitions, right? I could have infinitely many partitions and I want to let n go to infinity. And I find basically the largest one, which will be when n gets ridiculously large, okay, for this one. For this one, I want to do the reverse. This one, but I will let n go to infinity. As n goes to infinity, the partitions are going to be closer and closer to this one. So this one's getting smaller and smaller as n goes to infinity. This one will be getting smaller and smaller as n goes to infinity. And I call that the upper, did I do something? I call that the upper Darboux integral of f. And again, this sum is for sure squeezed between them. Okay, and basically now, okay, I'm in a position because now these two, this is equal to this. Oh, sorry, wait, no. Yeah, this is equal to this, but if I sum along I on both of them, right, if I sum along this, the equality will remain. This equality was true for any of the intervals. So it's true for all of them, right? So, I mean, at the same statement. So this here, right, is the same as this one here. So instead of me writing this, I'm going to write in this. But this can be simplified. So now we got to get another page. We got to write down what we have here. We got to go. Okay, so let's write down, let's recap, let's take our time. I know that the lower area, okay, for this partition, right, is less than or equal to the sum of f of zi times xi plus 1 minus xi. I goes from 0 to n minus 1, and then the upper goes from f to the partition. Yeah, and yeah, so basically, sorry. So this is true because of the argument I just made. Now, I also had from the mean value theorem that this piece was equal to capital F of xi minus capital F of xi plus 1 minus capital Fi minus 1. So if I sum over all of them, then the two sums will be equal, and I'm just going to replace this with capital F of xi plus 1 minus capital F of xi. And then that's less than this still. And the lower one. And now, okay, what I also said that this, okay, it must be the case, okay, that this was true of any partition, this inequality that I wrote here. Okay, now over all the partitions, you want to find the largest one such that the lower area is, you want to find the partition that maximizes this one. And we call that the lower Darboux integral. It's written like this, of f from a to b. And that is still guaranteed to be less than or equal to this sum over here. Because this sum, this applied for any partition. So it applies to even the largest partition for the lower bound, right? So it's fine. So f of xi plus 1 minus f of xi is less than. And now this one, the upper Darboux integral, is the smallest of all the upper areas that you could pick for any interval. So now what I'm going to do is I'm going to investigate this piece. This piece here, okay, if you look and you expand it out, you'll see that you're going to get a bunch of cancellation. So basically the sum I goes from 0 to n minus 1 of f of xi plus 1 minus f of xi, right? It's equal to, when I is 0, f of xi minus f of x naught plus f of x2 when I is 1 minus f of f of x1. And then you'll get these canceling out, right? Then the next one's going to be f of x3 minus f of x2. And then these will cancel out. And you'll do this, and you want to see what happens for the last few. So it's going to be n minus 2 is going to give you f of x. N minus 2 will be n minus 1, f of x minus 1, minus f of x n minus 2, but this will cancel with an imaginary thing here, plus then the last term is going to be when it's n minus 1, so it's just f of xn minus f of xn minus 1. And then these will cancel. And the only terms that you'll actually have are this and this. And then this is the same thing as f of xn minus f of x0. But these are the beginning and ending values of your interval. So this is just f of b minus f of a. And that's really nice because that actually starts to look like something that our theorem is trying to prove. And we're pretty much done at this point because essentially we want to go and remember what the actual definition of an integral is. And we actually say that the integral from a to b of f of x dx exists if and only if it equals the lower if and only if the lower Darboux integral equals the upper Darboux integral. So if this is true, then we say that the integral equals these two values, which match. And then, since it's the case that we have it where this integral is defined, these two values are indeed equal, which means that the integral equals those two values, and then this must equal that integral value. So the integral exists, we know that, so then therefore this must equal this, which forces this to be equal to all three as well, and you have your fundamental theorem.